Hello everyone, my name is Yosuke from Keio University, Japan. In this video, we're going to present our research titled A Learning-Based Wedge Thread Gating Mechanism for Simultaneous Multithreading Processor. This is abstract of our researches. In SMT processors, resource control mechanisms are essential to avoid resource conflicts. In order to attack the problem, fetch policies are conventionally used. However, fetch policies only have limited capability to avoid resource conflicts, since they are ignorant of resultant IPC due to their control. Accordingly, in order to maximize thread level parallelism in SMT processors with high thread counts, especially 4 or 8 threads, sophisticated control mechanism is essential. In this paper, we propose a fetch gate estimator that expands fetch policies to break the limitation of conventional policies. Unlike simple predictions such as perceptron-based branch predictor, the FGE adopts machine learning to control processor resources directly. Its learning models are implemented as a hardware mechanism and trained online in parallel with program execution. As an introduction to our researches, we will introduce the background and related works of our research, including simultaneous multithreading and resource conflicts in SMT processors. Simultaneous multithreading technology is widely adopted in modern processors. In SMT processors, multiple threads share hardware resources with each other. Each thread frequently stalled due to data dependencies. In the left side figure, which shows superscalar processor pipeline, these idle cycles degrade hardware utilization. On the other hand, in SMT processors, multiple threads hide latency of other threads to achieve significantly higher hardware utilization over single-thread superscalar processors. Sharing resources with multiple threads causes side effects as well. On some outstanding events, resource conflicts between threads occurs, which leads to degradation of processor performances. Data cache misses and branch mispredictions are two major examples of the events. In order to achieve better performances in SMT processors, sophisticated resource control is essential. It is more critical for processors with more than 2 hardware threads, such as server processors, which demands very high thread level parallelism, or high-end embedded processors that use hardware threads as task queues to reduce context switches. Since occurrence of resource conflicts are dependent on combination of applications running in simultaneous threads, acquiring optimal control becomes more and more difficult when the number of hardware threads increases. For resource management in SMT processors, instruction fetch policies are conventionally used. Fetch policies control instruction fetches based on certain resource usages. Fetch policies take mainly 2 actions for fetch thread control: prioritization and fetch gate. Prioritization simply prioritizes instruction fetches from certain threads. For example, ICount favors threads with fewer in-flight instructions, and fetch gate suspends fetches from inefficient threads. For example, FPG stops fetches from threads with many incompetent branch predictions. Conventionally, fetch policies are only simple heuristics, and therefore have problems. Fetch policy only monitors single type of events, and they are ignorant of resulted throughput by fetch control, and control takes effect only after an outstanding event occurs. For the processor with more than 2 threads, in which resource conflicts significantly affect total performance, better control scheme is required. Next, we show characteristics of resource contention that is monitored during SMT execution. Then we describe motivations of introducing learning algorithms. In order to observe resource contention in SMT processors, we conducted a preliminary evaluations. For the fetch policy, we used round robin, which is not aware of resource usages, and targeted 4-thread mixed workloads of compute-intensive and memory-intensive tasks. During the evaluation, we sampled average in-flight instruction counts and weighted IPC in 1,000 clock cycles for 500,000 clock cycle execution. This figure shows the evaluation results. X-axis is the average number of in-flight instructions, and Y-axis is weighted IPC. As the result shows, tasks in 2 loops showed totally different properties. While memory-intensive tasks tend to keep stable weighted IPC. Weighted IPC of compute-intensive tasks were very sensitive to in-flight instruction counts. Memory-intensive tasks frequently stalls due to data cache misses, leading to monopolization of instruction queues. And the compute-intensive tasks are bothered by those tasks. As two groups show different characteristics, it is possible to identify compute-intensive tasks and memory-intensive tasks with binary classification. Two groups can be roughly separated by the red line in the figure. Left side of the boundary or compute-intensive threads are scheduled by conventional fetch policy, such as ICount. On the other hand, right side of the boundary or memory-intensive threads are fetch-gated until lossless conflicts are resolved. Based on the idea, we introduced a learning algorithm for fetch control. Next, we explain about our proposal, a fetch-gate estimator, which is an instance of resource control mechanism based on a machine learning algorithm. The fetch-gate estimator, FGE, is a fetch-gate mechanism that is built using single-layer perceptron. It works in combined with conventional prioritization fetch policies. All of the inference and training mechanisms are implemented as hardware modules. Training is performance online and dynamically adapted to workloads, so the characteristics and resource demands of threads are encoded into learning models. Training signals are generated based on performance targets to tune control quality of the FCE. In this research, we especially targeted fairness of resource distribution and reduction of wasted instructions. This is the architecture diagram of the FCE. It is consisted of 4 components. First one is the gated thread inference unit, whose perceptron estimates threads that should be gated. Second unit is a thread select that selects a thread to fetch instructions from, combining conventional prioritization policies and perceptron outputs. Third unit is a weight train unit that calculates update value of weight. And fourth unit is a weight table to hold parameters for learning models. We explain gated thread inference unit and weight train unit in detail. Gated thread inference unit identifies inefficient threads that should be gated using perceptrons. We selected in-flight instructions, data cache misses, and incompetent branches as input of FCE. These inputs are reported to be useful to meet 2 performance goals, namely in-flight instructions and data cache misses are used for fairness of resource distribution, and the number of incompetent branches are used for reduction of wasted instructions. Perceptron outputs prediction results. That follows an ordinary equation of a single-layer perceptron, shown in this page. Threads with perceptron output value 1 are gated from the instruction fetch, and thread select unit determines one fetch thread from the threads with output value 0, using prioritization policy such as round robin or ICount. Weight train unit collects execution statistics and periodically updates weights. It operates in mainly 3 phases. Firstly, it executes instructions for certain clock cycles. This period is treated as one epoch of training. During the execution, this unit collects statistics necessary for training, such as input signals, prediction results of FCE, IPC, and wasted instruction counts. Secondly, training signal generator generates training signals, which we explain in the next slide. In accordance with prediction, 0 not gated or 1 gated is fed back as a training signal. Thirdly, weight train unit calculates error and updates weights, then restarts from the first phase. Training signals are generated in training signal generator, which is located in the weight train unit. As the training signals are fed back to the learning models, how the training signals are generated decides the resulted quality of control. So the training of the FGE is controlled by training signal generator policies to reflect a wide range of QoS target to fetch control. In this paper, we focus on fairness of resource control and instruction loss reductions. In order to achieve the former goal, this unit selects a thread with the highest weighted IPC for the gated thread every epoch. And for the latter goal, threads with more squashed instruction than predefined thresholds are trained to be gated threads. Next, we conducted performance, logic review, and timing analysis of our proposal. We describe evaluation setups and results. We implement the FGE in Responsive Multithreaded Processing Unit, RMTPU, using Verilog HDR. The processor is an embedded processor for real-time systems and implements various features to support real-time processing. The processor adopts 8-way prioritized SMT, which executes 8 threads simultaneously, and resources are controlled based on priority assigned to each thread. In this paper, RMTPU ignores the priority to work as a normal SMT processor. FGE is implemented in the fetch thread sector that is highlighted in the red box. Parameters of RMTPU are as shown in the table. Most of the parameters follow processors in the references. On the other hand, linear registers and reorder buffers are observed to be bottleneck in original configurations. So the capacity of these modules are expanded to reduce excessive resource conflicts. Task sets of performance evaluations are selected from my bench. Benchmarks are categorized into 2 groups, ILP and MEM, depends on its cache miss rates. And workloads used for evaluations are composed of 4 and 8 tasks that run simultaneously in the SMT processor. Mixed workloads are consisted of tasks from 2 groups. List of workloads are shown in the table. Benchmarks with blue highlights have many branch mispredictions, and ones with red highlights are second instances of duplicate benchmarks within a workload. We use 3 metrics for performance evaluations. First one is total IPC, that is simply sum of IPC of all threads. Second one is harmonic mean of weighted IPC, or called Hmean, that is commonly used for fairness and throughput analysis. Third one is the number of squashed instructions from long branch paths. Then we evaluated 2 baseline policies, round robin, I count, and 2 proposed mechanisms, FGE combined with RR and I count. This figure shows evaluation results of total IPC of each workload. We discussed the results of 3 categories in detail. First of all, FGE worked for mixed workloads very well. Especially in Mix 4.2, total IPC improved by 98.9% over I count. In Mix 4.2, one benchmark has high single-thread IPC, while it requires many entries in instruction queues. This task is discriminated in I count. However, FGE prioritized this task, considering resource demands captured in the learning model. For the MEM workloads, FGE were capable of extracting parallelism for most of workloads. As for the mix, a part of compute-intensive phases in memory-intensive tasks are prioritized by the FGEs. In contrast to MEM and mix, FGE did not work appropriately for ILP workloads. The reason for the degradation is that the training signal generation policies were too pessimistic. Since the policies select at least one thread to be gated at every epoch, excessive fetch gate occurred when fetch bandwidth is a bottleneck in ILP workloads. By devising the training signal generation, throughput will improve at least as high as I count. This graph shows evaluation result of Hmean. Hmean result mostly follows the result of total IPC evaluations. While FGE did not work well for ILP workflows, for the MEM and mixed workflows, all of the task sets showed Hmean improvements, which means FGE work well to improve both throughput and fairness for these 2 types. This graph shows the squashed instructions that are executed from long branch paths. In most cases, FGE could identify threads with incompetent branches and stop fetches from them so that instruction loss decreased. FGE based on round robin and FGE based on I count reduced 21% and 15.9% of instruction loss compared to respective base policies. We synthesized RMTPU as well as proposed design using Synopsys Design Compiler with TSMC 130 nanometer process library, and we calculated relative overhead of our design with CPU front-end of RMTPU and entire RMTPU that implements baseline round-robin fetch policy. For timing constraint of synthesis, we set minimal latency that each design can achieve. And for RMTPU and CPU front-end, we set 10 nanometer second, which is operating frequency of a processor in reference 16. Synthesis results are shown in the table. Area overhead of both FGE with round robin and FGE with eye count was not so large, which is at most 1% of the CPU, whereas the critical path in FGE and not bottlenecks in RMTPU. Pipeline registers are required for the FGE to operate at higher frequency. Major critical paths in FGEs are in other trees in the perceptrons. Accordingly, pipeline registers are required to shorten critical paths. As the pipeline stage increases, it takes longer for the outstanding events monitored in performance counters to be reflected for control. So we evaluated performance changes with different pipeline stages from 1 to 4. One stage means there is no pipeline registers, which is a baseline used for formal evaluations. Evaluation results for 3 workloads with different pipeline stages are shown in the figure. Difference of total IPC from the baseline one-stage design is depicted. As the figure shows, observed performance loss was at most 0.5%. This is because characteristics of each thread are encoded in FGE, which allowed FGE to get inefficient threads even before outstanding events occur. Therefore, adding more pipelines registered for FGE only has minor damages for performance. Now FGE can operate at higher frequency. Lastly, we conclude this proposal and discuss future works. In this presentation, we propose fetch gate estimator that introduces machine learning for fetch control to reflect resource demands from workloads. It also optimizes fetch control based on resulted IPC. As a result, the FGE achieved 7.78% to 39.1% Hmean improvement in mixed workloads of compute and memory-intensive tasks, while reducing wasted instruction from long branch paths by 15.9% to 21% on average. For the future works, we are going to improve training signal generation policies to improve ILP workloads. And we are going to adopt multiple layer perceptron to investigate performance impacts. Then we are also planning to extend learning-based control for other pipeline stages, such as instruction issue and commits. Thank you for listening. This is references of this presentation.